Swayam Prabha. Digital India. Educated India.
We are on the lecture series on advanced hydraulics, part of the postgraduate courses in civil engineering for the NPTEL program development. So, we are going through the third module on varied flows for last few classes. In the last class, we had discussed on the standard step method to solve the dynamic equation for gradually varied flow. We have seen that this method is very much suitable for non-prismatic channels. For prismatic channels, we have already seen the other methods of solving dynamic equation. We have also discussed on the methodology to solve using the standard step method. We have discussed it elaborately, although we have not solved a problem, but we have discussed the methodology on how to solve that problem and all. After that, we had given a brief introduction on spatially varied flows. So, today we will be elaborately discussing on spatially varied flow. So, as discussed in the last class, spatially varied flow means it is a non-uniform discharge due to the addition or deduction of water during the course of flow from one reach to another reach. So, like this, when it flows in this direction, some more quantities of water are getting added and the uniform flow entirely becomes non-uniform. So, such type of flows are called spatially varied flow. We have seen that there are two types of spatially varied flow, that is flow with increasing discharge in the reach in the flow. If the channel flow is in this direction and if some quantity gets added into the channel in that reach, this is called increasing flow with increasing discharge. This is flow with increasing discharge. And flow with decreasing discharge, when the flow occurs from this direction to from the upstream to downstream, some quantity gets deducted as seen here. This is flow with decreasing discharge. You can also see some more examples of spatially varied flow, especially if there is a gutter, road gutter or a roof gutter. Water from the roofs and all, they flow in these directions and gets collected in this channel, in this gutter, and the predominant direction of flow in the gutter is this. So, here in this entire roof is collecting water and draining into this channel. So, the flow occurs in this main channel like that. It is also a spatially varied flow. You can imagine several types of flow. Here the cross section may be like this. If you look into that, flow occurs in these directions and the channel cross section is of the following form. The assumptions involved for developing dynamic equation for spatially varied flow, we have discussed that in the last class. We suggested that the flow is unidirectional, it means velocity distribution across the channel section may be taken as constant, so that we may approximate various places alpha and beta as 1 and all. Pressure in the flow is hydrostatic, slope of the channel is relatively small. Manning's formula is used for computing friction slope and friction loss. Effect of air entrainment is neglected. These things we discussed in the last class. Now, to derive the dynamic equation for spatially varied flow, as shown here, this is a three-dimensional view of the channel, some quantity is getting added here. If I take a longitudinal view from this thing, a datum line is there, this is the channel bed, water surface line. I am taking a control volume between two sections 1 and section 2. So, that entire control volume is elaborately shown here in the magnified form here. So, this is section 1, section 2. So, you can see some quantities of water is getting added along the reach of that control volume. So, we will derive the continuity we will derive the equations, governing equations that are required to obtain the dynamic equation, or the governing equations that are called dynamic equations for specially varied flow. So, as seen in the channel, so the quantity increases, the quantity is increasing along the reach of this channel. So, let me suggest that this is Q star, it is increasing, the quantity is increased at a rate of Q star, that is Q star is the volume or it is the discharge per unit length of the reach that is getting added into the channel. So, if you take it like that, Q star quantity is getting added here. Now, as the phenomenon here, we have suggested that this quantity it is increasing Q star, it is a uniform rate, this discharge per unit length it is a uniform rate and it is adding equally. So, we are assuming that the entire process is now in a steady state condition, whatever inflow is coming into the control section, whatever is going out and whatever is adding into the control volume, all those quantities they are now in a steady state. So, we are suggesting that the flow is predominantly in one in this direction, the flow direction is one unidimensional or one dimensional. To develop the continuity equation, for such a situation, we use Reynolds transport theorem. We have already discussed about RTT in earlier lectures also. So, I am not going to discuss further on that. So, if you recall the Reynolds transport theorem, the equation for Reynolds transport theorem suggests that the material derivative of any extensive property capital B, that is dB by dt, this is equal to dou by dou t of that control volume, whichever control volume you are taking into account, beta rho du plus integral area beta rho v dot n dA, where this quantity, the first term we suggested that it is the rate of change of the extensive property stored inside the control volume, and this is the net outflow of the extensive property across the control surfaces of the control volume. We suggested that beta is intensive property. So, let us take B is equal to mass of water in that control volume. So, when we took this mass as the control volume, so you know that in this control volume B is equal to mass, I can suggest that mass can neither be created nor be destroyed. So, this quantity will be 0. Now, as the entire process is steady state condition, this also becomes 0. We have the net outflow from the control surfaces, which has to match. So, I will write it the following form: 0 is equal to dou by dou t of, small beta is equal to 1 for mass. So, I am writing it rho du plus rho v at this section, on this left hand side section 1, section 1 1, this is section 2 2. Here the properties are V, the average velocity is V, area is A, discharge is Q. Here we are suggesting that this is, say we are assuming the control volume is having a reach length of del x. So, V plus dou V by dou x into del x, then area we are considering A plus dou A by dou x into del x, and Q we are suggesting Q plus dou Q by dou x into del x. Like that we are suggesting the properties at each sections. So, here I can write now dou rho V plus dou V by dou x into del x A plus dou A by dou x into del x. So, this is the entire outflow. Then as V dot n, the vector means the quantity V dot n in the expression, V dot n is negative for the inflow conditions. So, we are suggesting that minus sign here. So, rho V A in the inflow, then what are the quantities? We have rho q star into del x, some quantity is getting added through the top also, that is also incorporated here. So, we have 0 is equal to, you just rearrange the terms here, 0 is equal to V bar dou A by dou x into del x plus A dou V bar by dou x into del x plus some higher order terms, higher differential terms, see del x square minus q star del x. Here what we are going to do is that we are going to neglect higher order terms, wherever these things are coming we are going to neglect them. So, this expression now changes into q star is equal to V bar dou A by dou x plus A dou V bar by dou x. So, this from the continuity equation we are going to get the expression q star, that is the discharge per unit length that is getting added or directed in the specially varied flow along the ridge, that is small q star. So, from the continuity equation we are getting this particular expression. If you closely watch that, you know V A is equal to the discharge at any section q. So, this quantity is nothing but q star is actually dou by dou x of V A, that is dou by dou x of q. So, I can suggest that q star is nothing but dou q by dou x. So, this will be a useful expression, later on we will be using it extensively. Now, let us go for the momentum equation. So, we are deriving for increasing flow. So, in the earlier class we mentioned that for increasing discharge we will be using momentum equations. So, we are for increasing discharge. We are deriving for increasing discharge or spatially varied flow. So, again the Reynolds transport theorem, we will be going to use them. Beta rho du plus control section beta rho v dot n dA. Now, in this case the extensive property B is equal to momentum and intensive property beta is equal to, it will come out to be velocity, because momentum divided by mass will give you velocity. So, that you have to note it. So, based on that thing I can just suggest now the following thing. This is the bed slope. Let this be the depth y 1 at section 1 1, y 2 at section 2 2. They are separated by a del x. This is the control volume, earlier we suggested. We are having an increasing discharge at rate q star per unit length, having flow. So, the net outflow according to this equation. So, this is the net outflux of momentum across the control surfaces. What are they? That we have to analyze. This is the rate of change of momentum, that will give you rate of change of momentum. So, that will give you the net force. Net force in the system or in the control volume. So, based on these principles we are going to give the momentum equation here. So, small beta is equal to V. So, now the net outflux of momentum, I can write it. Just recall in the continuity equation in a similar form. So, we will be using the thing net outflux of momentum across the control surfaces. This is equal to, first we are writing the outflux, dou v by dou x into del x into rho q plus dou q by dou x into del x. That I can replace it, that is, if you recall, dou q by dou x is nothing but q star. So, I have just replaced it by q star, then minus in the inflow section V rho q. So, the whichever section, here the section will be like this, here the section will be like this, whatever area is there, we are taking the average velocity in these sections. So, that is why I am putting the bar here. So, V rho q is the inflow momentum, influx of momentum, and this quantity is the outflux of momentum. So, I can now easily write this quantity as rho dou v by dou x del x into q plus q star rho dou v by dou x del x squared plus rho v q star del x. So, as we mentioned earlier, we are going to neglect the higher order terms. Higher order terms, these quantities we are going to neglect. So, we will get the expression for net outflux of momentum as rho q dou v bar by dou x into del x plus rho v bar q star del x. So, the left hand side of Reynolds transport theorem equation, it consists of the material derivative dB by dt. So, this is nothing but the net force in the system. So, in the net forces for this control volume, whichever control volume you are going to take into picture. So, in this control volume, the net forces are, means the types of forces are body forces and surface forces. So, forces are of the type body forces and surface forces. Surface forces. So, these what are the things? It has controlled surfaces. So, whatever forces acts on the controlled surfaces, they are called surface forces. Whatever forces are there inside the control volume, they are suggested as body forces. So, you can easily suggest, means you can now remember them, that is the body force in this control volume is nothing but weight of water in the control volume, right. This is the body force or the component or whichever, due to the weight of water, what is the force in the flow direction, that we have to take into account. Surface forces in the control volume, it may be developed due to friction, it may also be developed due to pressure exerted by the adjacent liquids on the walls of the control volume or on the control surfaces. So, we have to take into account all these forces and obtain the net force. So, let me ask you, what is the weight of water? What could be the weight of water? So, if you have such a control volume, here it is A and here the area is dou A by dou x into del x, then the weight of water is nothing but density of water into acceleration due to gravity A plus dou A by dou x into del x. So, we are taking the average area between this portion and this portion. So, somewhere here that is being taken into the length del x. So, I can write this as rho g A plus half of dou A by dou x into del x into del x. So, the component of, as there is a bed slope and the flow of liquid is in this direction predominantly, we need to find the, actually we are we have to find the net force in the flow direction. Therefore, the component of weight of water that is available in the flow direction, that can be obtained as component of weight of water in flow direction. If you are giving the weight as W, then this is nothing but W sin theta, and sin theta, you know, slope of the bed, Therefore, this is nothing but W S 0 is equal to rho g S naught A plus half dou A by dou x into del x into del x. So, this can be approximated wherever del x higher order of del x terms are coming, we can neglect them. This can be approximated as rho g S naught A into del x. So, this is your component of weight of water in the flow direction. How will you obtain the two surface forces, friction and pressure? So, the friction, first consider friction. Friction head between two sections. According to our theory, this is nothing but friction slope into length of the reach. So, that is SF into del x. This is your friction head HF. SF, you know, it is obtained using Manning's equation. It is nothing but V squared N squared by R to the power of 4 by 3, or it can be given as Q squared N squared by A squared R to the power of 4 by 3. So, how do you compute friction force? Say, you know that friction force along the any reach of the channel, you have the following reach of the channel. So, there are wetted perimeters. So, there are wetted perimeters, and all along that wetted area the friction force will be acting, and it has been obtained through chassis earlier in the uniform flow and all approximations, uniform flow approximations and all. At that time, we have suggested that the entire concept, the entire friction force, it can be approximated, that is friction force can be approximated in such a way that you can first compute pressure due to friction head, that is friction head whichever we are computing, this HF into the average area of flow section. This was approximated. So, based on the same thing, I can now write as friction force is equal to FF is equal to what is the pressure due to friction head? It will be rho g HF, and the average area, you can recall that it can be given as A plus half dou A by dou x into del x. So, this is your average area. So, friction force I can write it like this. This you can easily now approximate SF into del x into A, whatever quantities above that are there, that is del x into del x terms, higher orders of del x terms, we are omitting them. So, this can be approximated. I can write it again. Friction force is equal to rho g SF A into del x. So, we got the weight component, we got the friction force. Now, next remaining is the pressure force, force due to pressure. So, for any cross section, if you recall, how did you compute the pressure due to, how did you compute the force due to pressure? Say if this is the water level, then you have suggested that whatever is the centroid of this area, that is height to the centroid of the area from the top, if we give it as z bar. Then the pressure, the force due to pressure in this can be given as the pressure computed at this centroid into the area of the cross section. So, like that. So, it can be suggested that head or what is the pressure due to this thing, rho g z bar is the pressure into area. So, this will give you the pressure force in any cross section. So, similarly, at inflow section, let me suggest that it is having this depth to the centroid is z bar. So, f p 1 I am giving it as rho g z bar into A. Similarly, at outflow section, so area may increase or may decrease, but let us assume that it has increased by a quantity dA. The area has increased by a quantity dA, and the height or the change in water elevation is dy. Let us assume for this between the reach del x, that is we have the two sections separated by a distance del x. So, as we have recalled earlier, here also the pressure at the centroid of this area, at centroid of area into area will give you the pressure force. So, F P 2 I am computing in the following form. This is nothing but rho g into, earlier it was z bar plus dy into A plus rho g, whatever change in area means how much area it is being there. This is elevated by dy, isn't it? And that increase in area is d. So, dA into dy by 2, that will be the force created there due to pressure in that location. So, I can compute, add them, I can approximate now this quantity neglecting higher differential orders. This as rho g z bar plus dy into A. So, you have now net forces in the system. Net forces in the system, you have sigma f is equal to w sin theta minus f f plus f p 1 minus f p 2. You know the pressure force in the section 2, it will be acting in the opposing direction of the flow. That is the concepts we have already learned earlier also. So, these things can be rearranged, rho g s naught A into del x minus rho g A s f into del x plus rho g z bar. If you look into f p 1 minus f p 2, this will be given by the following two terms, z bar plus dy A. So, the net force sigma f is equal to rho g s naught minus s f into A into del x minus rho g A into dy. So, according to the Reynolds transport theorem or the conservation of momentum equation, the net force should be equal to the rate of change of momentum, that is given as the net outflux of the momentum. So, you equate them both, we will be having net outflux of momentum. If you recall them, we had earlier given that as rho q dou v bar by dou x into del x plus rho v bar q star into del x. So, these two quantities 1 and 2, they have to be equated, equate 1 and 2. So, we will get the following expression: rho q dou v bar by dou x into del x plus rho v bar q star del x. This is nothing but equal to rho g S naught minus S f A into del x minus rho g A into dy. So, you can easily take rho terms out, as this is an equation now. You can, and you are dealing with incompressible liquid. So, we can take rho easily out of this equation. This equation gets simplified into q dou v by dou x into del x plus v q star into del x equal to g a into S naught minus S f del x minus g a dy. Rearrange the terms. You may do them yourself also, but however, I am just writing it for your benefit. Dou q by dou x into del x is equal to S0 minus SF del x minus dy. I hope you understood why I wrote this term as dou q by dou x. Q star I have just converted to dou q by dou x, so that this expression we will get in a better way. So, subsequently I can now write the following terms: dy is equal to S0 minus SF into del x minus 1 by G A. What is this term? Q dou v by dou x plus v dou q by dou x. This is nothing but dou by dou x of q into v, right. So, that benefit I am getting here when I write it in the following form. You see, as del x is the elemental length of the reach, if we are going to limit del x, then and putting it into the denominator. So, we will suggest that taking limits, this can be suggested, del x tends to 0 limit. This can be now represented as dy by dx is equal to S0 minus SF minus 1 by G A dou by dou x of